So, I would like to continue with our lecture on smart energy distribution. So we have just looked at the left part of that. Let's see. Yes. It also means that all the, I don't know, maybe it's still there. Maybe the annotations are still there, but I don't know. I'm afraid the annotations are all gone that I made today. Yes, it's all gone. That's a pity, but things like that happen. Okay. So, I close that, go there again. Where have we been? At organic computing. This was our slide. Let's try it again. So, it's good that it's all recorded, so we have all the devices, all the things there. So now we look at the right part, the control, and there we have, we get the situation from from the observer, and then the situation parameter is sent to some kind of mapping device. Why do we need that? We would like to respond to a certain situation, and so we need to be able to look at a certain situation. There are certain conditions that are formulated, for example. So this is just one possibility. At least we have certain situations which are coded in some way, and they are mapped to certain actions. It may be that several actions are triggered if we have a certain situation, and then we would like to choose the best one. That's why it says here an action selector. We would have to decide which action has to be taken in a certain situation, and this should be done fast, almost in real time. So this cycle from observing to finding out what has to be done should be very fast, almost real time. It may be that it's not exactly real time, but it should be very fast. And now we would like to know whether what we have selected as an action actually is adequate. So how can we find out about that? We just store which actions we have selected. We store what we have seen before, like the situation that actually led to selecting that action. And then at some later time, like this is the current situation, is also sent to that element there. We compare the difference between the old situation where we have selected a certain action and what actually was changed by executing that action. Because we wanted to have a certain effect, otherwise we wouldn't have needed such an action. We would like to observe what has happened due to executing that action, and then we have had some predicted response, and if that is different, like if the effect is different from what you have expected, then we would say that's a bad action. Nevertheless, or in any way, we will get some kind of fitness of that action in the situation where we have selected it. And so we can give some, or associate some kind of fitness value to that action in that situation, and this can lead to some adaptation in that mapping module. That means the next time we will have this situation, maybe this selection will be different if the action that we have selected was performing badly. Then we would indicate that, so the next time we might choose a different action. And now there are situations where it is not adequate to just test out, for example, any new action and take the risk of something bad happening. For example, in the traffic light controller, you must make sure that nothing happens which can lead to an accident, for example. So for that, we have a simulation model. And then for a situation where we are not satisfied with the currently available actions, we would just, based on the simulation model, generate new actions by some device there or some method that is implemented there. And there we would evaluate the potential new actions based on the simulation model. And if we have found something which is good, we would move that down into the mapping and then have a better response to the situations that are observed. And so in this way, this system would learn about the fitness of the actions that are selected. It would also be able to improve its behavior, but by generating new actions for situations that had not been there before, or where the currently available actions don't perform well enough. And for that, we need an adequate simulation model. You could immediately say, how do we know that the simulation model is adequate? This is an assumption that we just make. If necessary, this would have to be changed. Okay, and then we have the user who's providing objectives and who would like to also look at this current situation or this current status in that system. So in this controller, we have the mapping. This component, we have to evaluate what we have done. We should be able to adapt the way we respond, and this is directed based on the goals and objectives that are given by the user. So this is this generic observer-controller system, and you might see that we have used exactly that in the organic smart home architecture. But in some hierarchical way, we had the observers and controllers of the devices, and then on top of that, we had the global observer and controller. Now, one could view at that in a slightly different way. One could say, okay, we have here our system and observation and control, which could be a traffic light or an energy system. And there we have some built-in controller, which we have actually adjusted this way. So that's real-time response. And then we have this next layer where we notice something has changed. We have to respond to a certain new situation. And so we look up our rule set in the controller to find out what has to be done on the system. So this is one way of responding to situations that we observe in the system. And then on top of that, we have the possibility to actually generate new actions, not just select and evaluate, but also generate new actions. For that, for example, you could have an evolutionary algorithm which generates new actions and then which also evaluates them based on a simulator. And a new rule would then be moved down into the controller on the first level into that rule set. And in this way, we would have architecture which could respond to changing requirements, for example, by generating new actions, but which could also respond to slight changes in the environment and modify the way we select actions. Now, these two ways of doing that could be called online learning and offline learning. Online learning, because here we would learn from observing what happens if we select a certain action, and then we can evaluate that. We learn by experience. And offline learning means we have this simulation model, and we can offline evaluate potential responses to a new situation, and then move that into the online world. Yeah, so this is something. If you look into literature on architectures for self-organizing systems, you very often find architectures which are separated into these layers. So this is something which is which we can find in many different areas in robotics, there's a model called so-called viable, I cannot read that really, I have to wipe that out. So a so-called viable system, that's actually an architecture for economics. In economic situations, architecture for self-organizing activities in economic situations. And there is a sense, plan, act, architecture, and robotics. So there are all kinds of different architectures, but they, in a sense, they have this architecture, like this layered, such a layered system. They don't all have this separation into online learning and offline learning loop. They don't have these explicitly mentioned components as we have in the observer controller architecture. So this is our generic architecture for organic computing, which can be used in different ways. It can be used in a centralized way, as you see, or you saw in this standard introductory slide there. Could be completely distributed. You just have intelligent agents which in some way communicate with each other and then will solve certain problems. Or you could have something which is a mixture. You have certain intelligent agents, or we had in our organic smart home the devices which have small observers controllers, and then we have a global observer controller on top of that, or you could again have some more generic hierarchical systems. So this is like where this is an adaptive system. This would be completely self-organizing, and here we would have something which we call controlled self-organizing. That means it can run on itself, by itself, just following its rules, its internal rules, but we can control and influence it on demand. Okay, so organic computing has been used for many different applications. I mentioned traffic control, traffic systems. It has been used in production systems, smart camera systems, in supervisor applications, network control like internet network control. Systems on chip have been equipped with organic computing systems, and we use it extensively now in energy management and control. So we have this architecture here simplified where we just show the observer controller. It's all been implemented in Java. It's freely available. It's a public license, so you can use that. But to use it, actually, you need advice from us. So it's not that easily used, but it's available. And then there are other approaches to having, for example, a standardized communication bus. That is by the company Kellendonk, or was in the e-energy program. It was designed, the e-energy bus. And there, like Kellendonk emphasized or focused on having different types of communication protocols, ZigBee, KNX, UPnP, different types of communication protocols, which in some way have all to be standardized. So they or more or less, they just specified an interface in XML, which is a standard interface to those devices in households or buildings or wherever such an energy management system has to be used. And then EBUS supports IP-based communication, and this can be the interface then to certain application scenarios. And so we just combined it into one architecture where we have the EBUS stack below our observer controller architecture. So more or less in between the device and our drivers. And then we have an architecture which is equipped also with the EBUS. Okay, but I don't go into the details of the EBUS, just to tell you that there is something like that. There are many, or several, I should say, protocol suggestions for appliances and households. we more or less say we should be able to accommodate different protocols and find out the relevant information and then have a standard way of using that information in our observer controller. Now this has been extended in our research group, actually not just to look at individual houses, but also into some integrated building management. So we say that we still have here some hardware abstraction layer, or you could also say an entity abstraction layer. So this is more or less the organic smart home architecture, but we could generalize that to an architecture which abstracts from certain entities. So this is the entity abstraction layer, the system that is actually being observed. And we could have several of those components or several of those devices. We could actually put them together and then have, on a higher level, again, an entity abstraction layer abstracting from those devices that we have here. We could combine those into a larger system and have now different systems which have some observer-controller interface and observe what's going on internally and can provide some information to the outside world. And again, we could have this entity abstraction layer and a connection to the next layer. And so what we actually say is that this architecture is in principle capable to combine or to provide a building energy management system. This is what I have just shown you. And these could be put together, several of them. And then a demand-side manager actually would have, for example, several houses or complete balancing group or a collection of houses, know what's going on in those houses, can abstract from that and optimize the performance of those houses based on the degrees of flexibility that the houses would provide. And then also the substations could be operated like that. By the way, there's this DCS. DCS says a data custodian service. What's that about? A data custodian service is necessary because we have to decide which data should be provided to the next layer. We don't want to provide every data, and so data, we have certain data which is necessary or which is used internally by the observer and controller, and then we have the data custodian service which is responsible for deciding which kind of data should be made available to the next layer. And this can be extended. We can also put several generators together, have some kind of virtual power plant, in principle, based on this architecture. Now you could say this is a hammer and the world, if you have a nice hammer, the world is full of nails. Yeah, so we just find places everywhere where we can use that. But it doesn't change the claim that this architecture is in principle capable of serving as a more generic architecture for these kind of energy-related scenarios with different types of entities, but we could always abstract from the specific properties just looking at the relevant information that we need to actually use the flexibility that are provided by those systems. And you could also say, okay, I don't have here an observer controller, but maybe that's a MAPE architecture, and maybe somewhere here there's a completely different architecture. As long as they provide an interface to the next layer, we can integrate that. So this is a rather flexible approach, and we have run, we have had several research papers on that also. One dissertation is finished on that, others are almost finished. So this is work in progress, developing this. Now, this is the architecture that we have. what do we want to do with that? We would like to optimize what's happening in the house. And one thing we could try to optimize is to optimize the degree of self-consumption of energy that is generated locally. So self-consumption and self-supply are two properties which are of interest. So we could have many different situations. For example, 100% self-consumption would be or could happen. There maybe we would even have need for more power from the grid. Then we would have only a limited self-supply but complete self-consumption. And here we have a situation on this part. Maybe we can completely satisfy the local demand. So we have 100% self-supply, but there's still some power which is fed into the grid, because not all the power that is generated on the rooftop is actually used locally. And the question certainly is that how we can make sure that we can always balance out local generation and local consumption. You remember my initial scenarios where we saw that sometimes you have voltage deviations because we have imbalances. If we can balance that out, this is what we would like to do, and for that we use the organic smart home architecture. We tested that on a lot of different scenarios, on real scenarios, on simulated scenarios, and what you can see here is the result of a simulation over all the weeks of a year. And so we have certain weather information, climate information over that year. And we know how much power is generated from PV cells. We have certain demand for heat. Demand for heat is satisfied by a micro combined heat and power plant. And we assume that we have a 5-person household with a typical demand of such a household. And we don't have batteries in this scenario. This could be added, could improve it actually. So we ran the system just based on a typical profile, and for that got the red curve. So meaning that we had here 40%, like 40% or almost 60% there in the peak, 60% self-supply from the rooftop. Now, if we just modified the use of appliances in the house and the use of the micro-combined heat and power plant, then we could improve that quite significantly from here 40% self-supply to 60% self-supply. So this is quite a significant increase. You see, it's always possible to increase that, just to show you what kind of things we do with that organic smart home architecture. We use it not just for explicit control of a house, but also for simulation studies, because there we can use that optimizer or the optimization facilities that we have built in there to actually optimize self-supply or self-consumption. So depending on the size of the panels you have on the rooftop and the load you have locally, self-consumption can be rather low, but that can also be optimized in that way. So this just shows you that just by modifying using the flexibility of appliances and controlling the combined heat and power plant, not just based on the heat demand, but also on the electricity demand, then we can improve the situation. Okay, Florian Allerding was the person who did that. He designed, in his doctoral project, he designed the organic smart home architecture. And he's working now with a very innovative company in that area, a company called Better Energy, which now come out with products in that area. Okay, and I would like to tell you how we actually optimize. So I said we can optimize in that generic architecture, but how do we do that? So we have devices where some are controlled by the user. You need user interaction to be able to actually know that they have to be scheduled. And we have other devices like the combined heat and power plant, which is a element which is continuously providing either heat or not either at the same time heat and power, but depending on the demand for heat or demand for power. And so there may be a so-called sub-problem for the washing machine where a basket full of laundry has to be washed by 6 p.m. Dishes should be done by 5 p.m. and the combined heat and power plant should run for 2 hours. And so these are sub-problems, as we call them. And then they should be optimized in a reasonable way, respecting the external signals and goals. Like external signals means price signals, load limits, and so on. And then we would like to get solutions for the washing machine, the dishwasher, and the combined heat and power plant, and then know when to run those devices. Yeah, we should get out from that optimizer explicit information when we should start those devices. And the essential part is the way we do the optimization here. So we have this scenario. There's the basket full of laundry is coming, put into the washing machine, and this results in an activity. This is noticed, and then this activity is translated into a sub-problem. And the same may happen at other places. The sub-problem is sent to the observer. Then we may get more of those sub-problems, and they are sent to the controller with the task to actually find optimal ways of using or of starting those devices, of operating those devices. So they have to be optimized, and afterwards, after they are optimized, the resulting starting points are communicated to the controllers of those appliances, and then we have here the new sub-problems, and they generate commands to start those devices. Okay. Now, how does this actually work, this optimizer? It is an evolutionary algorithm which, well, you know already what an evolutionary algorithm is. I've shown it to you when we talked about the self-organized balancing power. The question is, how do we represent our devices? So we do it here in a very simple way. We just use a binary representation for all those devices. And this, I said, a sub-problem is constructed from an activity. So what we do is we generate a bit vector of a certain length k. And this bit vector actually stores all the different decision alternatives that we have. So if we have a bit vector of length k, we have 2 to the k, let me call these decision alternatives. Maybe 2 to the k different minutes at which we could start our device. That means we have a certain, like the washing machine, we have filled it, and we said we provide 3 hours, or after 3 hours it should be finished. The washing process takes, let's say, 1 hour, so we have 2 hours as potential starting times. That means 120 hours, so in that case 7 bits would be sufficient. Then we have 128 different starting times, and that's the role of the bit vector. Indicate the decision alternative for that device. And then we have to know how we have to interpret every specific combination of bits here. If we have such a combination, what does it mean for the load profile, for example? So we have to provide a load profile for that device. It gets the k bits as input and provides a load profile based on those k bits. And in the end, what we need is a command for our device to start at a specific time. So that's the back transformation, a concrete solution or command to actually start our device. So, if we have, for example, a dishwasher, this is a typical profile of a dishwasher. We have a certain release time here. That's the release time of the component. We have a duration of the task. That's our duration. We have a deadline for the component. This is the deadline. It should be finished by that time. And so the latest finish or the latest starting time would be dj minus pj. And then we have a certain shift of starting time. So this is the degree of freedom. And we will have a certain time at which would actually start, for example, there. Then this will be the real or the time that is actually chosen based on all the information we have about the current situation in the house and in the energy system. So again, the k bits are obtained by dividing the degree of freedom that we have this time period with an appropriate resolution into different starting times, and then we can define the number of bits. Then we have this bit vector, and then we need the evaluation function, which is which has to resemble this load profile of the device, and the back transformation has to show that from such a bit combination here, we have to know what actually the starting time for that will be. So this is information. In this way, you could say this is some kind of plug and play scenario, or you could say plug and optimize, because every device, it's providing its own driver. It's a description of its capability, of its load profile. The optimization algorithm just needs essentially this bit vector. The optimization algorithm is only generating new bit combinations, and then these are evaluated. And from that, we find out, certainly by having several components which are evaluated, we get a global load profile and can evaluate that with respect to price and load constraints. So there's one more, that's the subproblem. And then we have here an example. If the release time is 2 p.m. And the value of the bit vector is the number of minutes, then if we have 6 bits, it would mean we have 63 different minutes that we can decide for. And so a bit vector 0, 1, 0, 0, 1, 1 would just be 19, would mean that we would start at 14, 19 minutes after the release time. So this is the way this is working. And now we have seen what we would do for an individual device. Here, actually, like 10 bits means we have many more decision alternatives here. Dishwasher, maybe 8 bits. Our combined heat and power plant is a bit more complex, has more things to be specified. And there we have actually 43 bits. Depends on the way we model our devices. And then this is put into one component. This is the individual for our optimizer. So this is now just a bit string. And then our evolutionary algorithm is operating on those bit strings, and every bit string certainly has to be evaluated. So how do we evaluate? We have our bit string, split that again into the different parts corresponding to our different subproblems. And so these are the different parts. Then we use our evaluation function for the individual subproblems to generate the load profiles of those 3 devices. And then they have to be combined into a combined load profile. That is the resulting load profile. This has to be evaluated. So we have the fitness function, we have the evaluation of the individual, and that's then our fitness of that individual, and then we select again, recombinate, and so on, and as soon as we are satisfied with what we have seen here, we are stopping. Looks as if I have to briefly recharge my pen. This is a strange system that the pens have to be recharged, but it works like that here. You have a question?
The fitness value depends on the external input, so price and stuff like that.
Yes, exactly. So we have the external information, we have the price, we have maybe power constraints, and the combined load profile from the individual devices is our resulting load profile for that day. There may be more information, so maybe that we have a predicted load profile for our house, maybe we have already scheduled some devices which are still running, and so we have to take them also into consideration. So all this has to be added up in that aggregated load profile, and then we get the evaluation, how beneficial that is, and we take the best string which is generated. Okay, so this is what we do here. We have to take the best individual of the last generation, and then we transform that back into concrete commands for our devices, and so then we find out the starting times for these elements. Okay. So this is how the optimizer is working. Yeah, so this is the informatics part, that we have a certain optimizer. It's a generic optimizer, which can be used in a very flexible way. Now some people say, well, you have so many, or you don't have that many devices, although you have seen there are quite a few bits that we have to put into our genetic code there. So it's not that easy to optimize that, but some people say we should actually do that not by meta-heuristic, but use exact optimizers. We have so powerful computers, we can optimize it exactly. But if you look at the exact, or if you look at the energy situation, usually at the moment where you actually use your devices, the situation is not exactly the one that you had before in your assumptions. So whenever you have a scenario where you know that there is some uncertainty about the operating environment of a certain device, and now you try to optimize the use of that device, it may be that you have selected an optimal solution for a specific situation, but in the exact situation that you have when it's running, if that is different, then maybe your behavior is not at all optimal, but you need something which is good enough, hopefully robust against deviations, and then you are satisfied. And so what we decided for is to have rather fast, good solutions from our evolutionary algorithm, and we have this very flexible way of adding new components. They just provide their subproblems. They define themselves the evaluation function, and in that way we have a very flexible optimization algorithm in that architecture. So it's not fixed to just one scenario. Okay. We have designed that in the scenario of the Energy Smart Home Lab, and then came up with an extension. We had the opportunity to build something which we call the House of Living Labs in the Research Center for Information Technology. So there we have a space of about 2,600 square meters, not just an apartment, but a lab space, office space, and meeting rooms and so on. And there are some living labs that have already been there: ambient assisted living, automotive, mobile IT, service robotics were already in the basement. And then we designed new living labs. And living lab means we have an opportunity to display certain research projects to show what we are doing in cooperation with companies. So we are actually working there. Our employees are working there in that research center, And companies can come, which are cooperating with us, and tell their customers and show them what they are doing and developing together with us. And so it's an interesting scenario for actually noticing what's going on in research and development. And we did that here, like we extended that with respect to new living labs for energy, for home, automation and mobility. And I will show you a little bit about that, which relates to the energy scenario. So, as I said, we have these living labs on the first floor, or the top floor of that building. We have a smart home again, slightly different from what we have on campus, because here it's in a part, or it's a few rooms in a building, not a container. And it is a combination of ambient assisted living and energy scenario. We have our living lab smart energy. We have a mobility lab, and actually we have there now a security lab, which was added to that. And we have an automation lab. We have some presentation areas. We will also go there. We can show you what kind of scenarios we have there. And we have offices there where the scientists are working. So this is a view on the house. We have solar panels on the rooftop. We have our living labs, and then we have all kinds of devices. We have power inverters. We actually, like these solar panels have 15 kilowatt peak, 3 times 5 kilowatt peak. So we have 3-phase, 3 times 5. We have a battery there, 30 kilowatt hours capacity. We have hot water tanks. We have a combined heat and power plant, which is the same as we have in the KIT Energy Smart Home Lab. So in the Energy Smart Home Lab, it is too large. Here, it is too small. So it is adequately sized for that building. But when there is more need or heavy need for heat, we need a condensing boiler, another device for providing heat. And so we have the hot water tank for that. And then we would also like to use our combined heat and power plant in the summer, but there you don't need heat, but you need cold water if you want to have air conditioning. And so we have an absorption chiller, which is actually transforming heat into cold water using the temperature differences. And so we can utilize the combined heat and power plant in winter and in summer. And in winter we need it for heating up for using the heating, for heating the building, and here in the summer for cooling the building. And okay, that's then this slide shows that this house actually is equipped also with quite a bit of sensors and different types of energy carriers. So we have electricity, we have warm water, cold water, we also have gas. And here in the top scenario, what we see is we have a meeting room, we have offices, and there we have radiators, we have computers, we have air conditioning, certain sensors on air quality, carbon dioxide concentration, and things like that. And all this can be used in some observation and management scenario for that building. Then we have this household or smart home scenario with household appliances, again gateways and sensors. And here we have, different from the smart home on campus, here we decided explicitly to use very different devices. So they are all talking different protocols, or quite different protocols. Some can talk at all, like this pot here for making hot water. That cannot provide any, or this is not intelligent at all, but it can be plugged into this smart plug. And then we can observe the load profile of that device. And we can talk with the plug. And the plug can tell us what kind of power consumption that device currently has. And we can control the plug. We can switch it on and off. And so even having a very dumb device doesn't matter. We have an intelligent plug, and that can make even devices which cannot communicate able to being used in such a scenario. Then we have all the devices in the basement, as I told you already, and we also have, which I did not have on the previous slide, is this element here, an insert heating element for heating up the water just from electricity and not from gas, either from the combined heat and power plant or the condensing boiler. So we can produce heat here either from power or from gas. Okay, so this is, you could say, a multimodal electricity system, or no, multimodal energy system, because we have heat, we have cold, we have gas, we have electricity, and we are integrating that into just one building and trying to manage that in the most reasonable way, using the flexibility potential of the different energy carriers. Again, here, these are some of those devices which should be managed by that energy management system. We also have to communicate with the utilities, distribution system operator, and so on, have to know the grid status, and have to communicate with the users in that house. And just to show you what kind of things have to be set up if you design something like that, we had to come up with the idea that we have the PV cells on the rooftop, we have our battery, and then we can just use or store the power that is generated on the rooftop in the battery, and at some later time we can send that power maybe into the grid, and we would like to get the fee for that. So we can sell it to the grid, and there are certain rates for photovoltaic power. There are other rates for power generated from combined heat and power plants. And there is no special regulation for getting power from a battery. This is not considered to be adequate. And we went with that to the Stadtwerke here, and they said, well, nice idea, but you cannot configure that such that we can actually find out how much power you have generated from the rooftop and fed into the grid, how much you have used locally, and so on, and how much you have used with the combined heat and power plant. There is one other scenario where they tried that and it did not work. And this is how it can work. Yeah, so it is actually, it's much more than you would actually need necessarily. So we have here, I think, something like 7 different smart metering systems, where we, like first here's the energy manager, like this is the inverter, and this makes sure that power from the PV generator is stored in the battery, and there's only power from the PV cells that is stored in the battery. You cannot store or get power from the grid and store that in the battery. This is not possible in this scenario. And that means that whenever we take power from the battery, it is solar power. Then we have to, like here's a line out, here's a generation counter. There's another one. We measure how much power was generated, and then we also need to measure how much power we have generated from our combined heat and power plant. Then we have some offices which are using power. We would like to find out how much power is actually consumed in the house or in these offices. There may be some other or some remaining consumers, so we have here another metering system which measures how much power actually is not consumed in the house, this is the remaining power, the surplus power that is not consumed in the house, and which is fed into the grid, which is just the power from the PV cells. Here is the power from the combined heat and power plant. This is always sent into the grid, and this is measuring the combined power that is completely moved into the grid or taken from the grid, consumed from the grid. So it's a bidirectional metering system. And this was accepted as a way of actually documenting which amount of power has been generated from different sources and consumed at different places. Very complex system, very expensive, but we just wanted to show how you could do that. And then we have the thermal infrastructure and the metering there. We have to measure how much gas we are using, how much heat we are generating, how much heat we are consuming. So there are all kinds of sensoring equipments, again, installed in the house, but that is much simpler. But as I said, we have our combined heat and power plant, we have the peak load burner, and this provides power into our warm water storage. And then we also need warm water for the absorption chiller. There it is transformed into cold water, which is stored in the cold water storage. And from there it is sent to the air conditioning devices in our meeting rooms. So there we don't have phase change material, but standard air conditioning systems. And then certainly we have the heating system where all the radiators are provided with heat, and then the building is heated. Okay, so that's thermal infrastructure, electric infrastructure, and here some specification. I've told you most of these things here. So the combined heat and power plant can provide 5.5 kilowatt electric, 12 kilowatt thermal. Absorption chiller provides 9 kilowatt thermal, and condensing boiler has 100 kilowatt, so that's because the complete building has to be heated up in the winter. And then there should be also some mobile energy storage by using electric vehicles. This so far is not connected, but we know how to do that, so it will be done in some time. And we have intelligent consumption. We have smart home scenario there. We can optimize that as we did that in the Energy Smart Home Lab on campus. And so we have this integrated energy management system across the whole House of Living Labs. And there we have many people who work there. So if the management of the energy there is not done properly, they are standing in front of our door and are complaining. And so this is quite a challenge to do something to actually run the system there and at the same time developing it further. That's what we are doing there. Now, as said, we are interested in actually looking at different devices. So we have all kinds of different devices here in the Energy Smart Home, in this House of Living Labs. We have devices communicating with Zigbee. For example, our smart plugs are doing that. From Plugwise, they have Zigbee communication. We have devices which communicate using KNX, standard home automation technology. We have a communication interface that is provided by General Electric, Habitech it's called. We have standard REST interface for web services. And so different types of communication protocols, and we are working on combining that using the EBUS standardization efforts. So this is providing possibility to integrate many different systems. We also redesigned our energy management panel. And I will not show, I could also go into the detailed menus here. I will do that when we are visiting the House of Living Labs. And so here what you see is that on the top part we have the electricity related menus, and here we have the thermal menus on that part. And so we have the here possibilities to look at the use of the or the power generation from the PV panels. We can look at how the battery is used. We can look at the history of how the state of charge is developing, and also here for like we can go on our smart home. We can look at all the individual devices. We can go to the or click on that menu there on that icon and get information on all the sensors on all the thermal sensoring data. So we look at how the temperature curves in the storage devices is developing, what kind of or how much heat we are using in the radiators and so on. And we can look at that at different resolutions in a very flexible way. It means that we are storing all the data from these different devices continuously in some database, and we display the information in this energy management panel, and then we allow to look at the history of that data on this time series at different resolutions. And you can imagine that this is quite a challenge to do that. Yeah, we have this stream of data, has to be stored continuously. We have to take the data and store it, needs large storage space. And then we have to be able to look at it at different time resolutions. Just get specific data, get it every second, every 15 minutes, maybe only data for one day and things like that. And all this has to be built into such an energy management panel such that we can actually provide this functionality to access the data in a very flexible way. Yeah, need special data formats, special database technologies and so on. So it looks simple if you just look at this, but if you look at the functionality that we provide here, this is quite a challenge on the way you actually manage and use the data. So I could also mention that we have this data life cycle lab energy, and there we are working exactly on those methods, how we can, technologies, what kind of storage you need if you want to do something like that, like generate data, store this data, provide access to the data in a flexible way to time series data and so on. Okay, and just one more remark on this. If you have such a presentation or such a view on the current energy system in your house or in this building, you see immediately that, for example, here there's a certain temperature in that storage, in that hot water storage. And we had quite a few situations where we noticed, or my assistants noticed, that the temperature all of a sudden on a rather cold day was just about 40 degrees or something, much too low. This immediately indicated something is wrong. And they went into the menus and could see how the temperature curves had developed, could immediately say which sensors had strange behavior, and then call the service company and tell them exactly what kind of situation is observable here. And they could immediately see, okay, that's the fault, we come and repair it. And we have another building of the FZI across the street, where they also have a quite large heating system. And there the maintenance costs are significantly higher, because if there the service company is coming, they have to come, they have to find out what could have happened. They don't have any data, any sensoring data from what happened in that house. And so they have to do some work to analyze the situation. And if they are lucky, they find out actually what has happened and have the appropriate way to repair. Whereas here, all the information is there. So this is something which is in particular important for predictive, I put that in parentheses, maintenance. So one could extend this with some features that, for example, you provide some capability to put an exclamation mark there or some special sign indicating, notice something bad has happened there. Or you could trigger automatically a message actually to the service company, something bad has happened there. So different ways of how you could use such a system where you have all kinds of information about what happened in such a house to improve the way you could do maintenance in that house. And this is something which is also a very active area of research and development, how we could improve the maintenance of technical devices in the industry, in buildings, certainly also in private houses. But this is of particular interest if you have certain important components in your, for example, production chain, and you must make sure that there are no faults, that you have 99.9 or something operating times. So you cannot afford to have a breakdown of some components, and for that usually you have fixed maintenance intervals, which are done like you estimate the average time between failures, and you would like to make sure that you don't have a failure, so you just get the next maintenance, the next service interval, or the next visit from your service people, just because they say, we want to prevent that something happens, so we just do a maintenance work there. If you have such a system, you notice when something is suspicious and you can respond to that, and so then you don't have these arbitrary maintenance intervals, but you have situation-dependent maintenance events, which is much, or which can be and will be much more efficient. Okay, so this is the energy management system that we have designed, our organic smart home, with an interface, which again, let me show that again, is an interface here, you notice, slightly different from the interface we have shown in the house. Imagine you have that in a factory. In a factory, you would have a different type of interface, because their engineers would be the persons who would look at that, and they would have different requirements on what they would like to see and what kind of information they would need to have to get the appropriate information about a certain situation, where they might also be requested to provide preferences for using certain devices in order to specify degrees of freedom, specify flexibility potentials. And so this kind of user interface has to be designed appropriately to the, or has to be designed appropriately to fit for the requirements of the specific users of that system. Yeah, and you will design these systems in very different ways depending on which kind of people will look at this kind or on this display of the energy situation. And so this has to be done in a way that you can configure it in a simple way and also change the appearance in reasonable ways. So this is also something we have, like there has been a PhD thesis on making this configurable, adaptable to different situations. And there's also one current PhD thesis on how to design in general those user interfaces. Okay, so what we see as the necessity for the future there is to have, like in the smart home environment again, if we talk about an organic smart home, we are concentrating on energy management and user interface or user interaction, and it would be reasonable to add more services for assistance, comfort, entertainment, and so on. Where these functionalities here, these things, can be bought on the market. So there are all kinds of systems available supporting or providing those services, and that has to be combined with the energy management system. And then we have something which is more valuable to provide that combined type of services. And then we have a gateway to the external system. And so just to repeat what kind of topics we are interested in here, you remember we have to look at the decentralized load management on different levels, on house level, building level, factory level, and so on, where we need some kind of adaptation of the energy demand to the grid, depending on the current state in the intraday trading. That would be real-time pricing, maybe negative prices. Yeah. We would like to maximize the local consumption of electricity, so that's self-consumption, self-supply. Just recently in one of our projects, or not just that, also at conferences, I heard that people said the idea to have batteries in individual buildings is a very bad idea, because the people will try to use those batteries to optimize the power consumption in their house. And it means they will try to get independent of the grid, and this is something which is undesirable. They should use, like if we put storage into the grid, we should use the storage in a way which is sensitive to the grid, and which is useful for the grid. And this would mean that the batteries are used in a different way under different objectives than under the objective to optimize the self-consumption in a house. And this is a conflict between different stakeholders, homeowners or building owners, and the distribution system operators. The distribution system operators would like to stabilize their grid. The homeowners would like to optimize their local energy scenario, and you need some kind of balancing between those different objectives. Okay, so we have different use cases for smart home, smart building, and smart office or smart factory. And as I said, the user interfaces will be different. The type of the type of visualization will be different. For example, assume you have a large building, office building. You have all kinds of offices here around that floor. Now, if you're sitting here, you're certainly interested in finding out what is the load profile of my office. But are you allowed to look at the load profile of your neighbor? Is your boss allowed to look at the load profiles of the individual desks or different individual offices? Or maybe is he only allowed to get the aggregated load of that floor? Yeah, so these are problems which also have to be addressed. Who actually has the right to access the individual load profiles at quite some low granularity? Look at the individual offices. Usually the Betriebsrat will interfere there and say this is not allowed. And then you have to find out if efficient or reasonable ways of displaying the information that is necessary to get to get some view on the current energy situation, and to get incentives on behaving appropriately in that situation. So smart building user interfaces have quite a few of different requirements than smart home interfaces, and in an office or in a factory that again will be different. So what about smart factories? So it says here efficient production processes with optimized usage of renewable energies, green production. Now, we had a conference with people from a large German car manufacturer about different types of research topics, and we discussed possibilities to optimize the energy consumption and energy flexibility in the production line, and the person responsible for the production line laughed loud and said, this is ridiculous, that we should consider the energy consumption or energy flexibility in the production line for cars. We are building cars and don't care about the energy. But meanwhile, this company has its own division responsible for energy management, and they are actually providing now services on the primary control market. And they are providing these services because they found out, with our help, that there are certain interesting demands for power, certain load profiles of devices, which actually don't disturb the production process, but can actually fluctuate in some way depending on the need on the primary control market. And so meanwhile they're offering several kinds of services to the outside and making money with their flexibility of their demand for electricity. And so it shows that it is possible to generate new products that can be used on the market to make money from flexibility in energy demand. But it is difficult to actually get access to that because traditionally production lines are optimized under completely different objectives than looking at the energy consumption. And so if this is put into that optimization process, it makes it more complex, but one has to make sure that you can optimize that, identify flexibility, and still have high productivity. We don't want to interfere with the productivity. Another point is that reduction of peak loads is in an industrial environment a very important topic. Because if you have a load profile over the year, which looks like that, you have one small peak, then you are charged, you're paying a large amount of money for that peak. This is the standard tariff for industrial scenarios, that it is a peak-oriented, a power-oriented tariff. And so there it is very important to reduce the peaks, to make sure that you have a very low power profile. Get rid of those peaks. And then, for example, you can, there are typical arguments why you get peaks. For example, all your information processing equipment is looking for updates at a specific time of the day. And so they may be more or less sleeping, and then at 2 in the morning they wake up and ask for updates. And at 2 in the morning you have a peak. And so if you would just randomize that, not start them all at 2, but start them at different times around 2 p.m., at 2 a.m. or whatever, you can prevent that peak from occurring. And so there are quite a few devices, like other devices, other test equipments test equipments in factories, which actually need a lot of power. If they are all run at the same time, you have a large peak. If you manage them in the way that you prevent those peaks from occurring, you can save a lot of money. And so there are many ways how you can actually save money in the industry, in industrial processes, by managing the energy in a reasonable way. And then there are more things. There are electricity system services, so to provide reactive power for stabilizing the voltage, and to provide operating reserve power, like, as I said, primary control and so on. So lots of use cases which have to be looked at, where you need intelligent systems to actually manage that. Topics, I've mentioned quite a few. Economical topics, we have the time-varying tariffs. By the way, just one more remark on this scenario where you have such a peak. Sometimes you would like to generate a peak, or it might be beneficial for the grid to generate peak consumption, because at times where you have negative prices, the grid operator is very happy if you would generate a peak. But you should not be charged for that. If you generate a peak because you generate or you consume more power just because it's necessary in the current grid situation, then if you have a peak-oriented tariff, you would be charged for that. And this would be a bad situation. That would be your new peak. So these things have to be changed in the way the tariff structures are done, that if you provide a grid service and generate a peak because of that, that cannot be taken as a peak in your consumption, which you are charged for in your energy bill. Okay, so these tariffs are an important point. There are load-based electricity tariffs, as I just said. Could also be that you have a tariff where, depending on the amount of load that you actually have, you have to pay a little bit more. Like the more you use, the more you have to pay. For the first kilowatt, just 30 cents, and then the next kilowatt, you have to pay 60 cents or something like that. Okay, then self-supply is important. Self-supply, self-consumption. So the question is how beneficial it is to have self-supply, but this is this will come automatically as soon as it is a business case to self-supply your house with energy you generate on your rooftop. Then you will do that, independent of whether that is good for the grid or not. You will just do it. And so we have to be able to cope with such situations. We have to be able to consider power grid requests, balancing of power, demand and supply. We have talked about that inside the house, but also regional, using this balancing, self-organized balancing power. And so we would like to have green supply. That's obvious. We have to look at in-house communication, all kinds of different communication systems. Actually, in the house there, we have also a communication system which is called an ocean. An ocean is a system where you have a device, for example, you have a switch, and by pushing the switch, you can transform the mechanical energy into electric energy, and this generates a signal which is sent to the controller, and then, for example, the light is switched on or off. And that means that in the switch here, you don't need any power supply. No battery, no cable leading to it. It's just a device which can transform the mechanical power into electricity, and then you have the possibility to communicate. That means you don't need any wiring to be able to communicate in a house. One topic which we look at in the FZI Research Center is that in spite of having, for example, on campus this highly equipped house, or also in the House of Living Labs, many different communication systems, we have to look at technologies which we can gradually move into the houses, into existing apartments, and make them slightly more intelligent. One way of doing that is to use smart plugs, for example, because then even non-intelligent devices can be used in an intelligent way. So this is something which is important for the change management from the old systems to the new systems. We will not build everything anew, but we have to transform the existing systems in a reliable way. And then what we also do is that we test prototypes in different scenarios. So we are actually in the moment testing new products for the energy market in that FZI House of Living Labs, testing that under different scenarios to find out whether that is fit for being used in the real world. What else can I tell you here? We have these different sensors, actuators, as I said, and what one should do is to combine it with safety and security features. So we always also have to look at the security properties of our devices. As I mentioned several times, if we look at the or if we put more information processing into these scenarios, there is more opportunity to attack those systems, and we have to prevent that. We have to protect ourselves against the potential attacks from outside, make sure that our systems are safe and robust against those attacks. Okay. We also want to provide that or put that energy management, that local energy management, into a larger system. So we have some demand side manager which will use our flexibility potential, and there is a network control system which will actually be able to control the way our components are used or how the system actually is stabilized. A demand side manager needs information on what kind of demand management is necessary in the moment, what kind of opportunities are on the market to sell a surplus of power or to sell flexibility. And it means that you need a combination of the of markets, demand side managers, and network control systems like the distribution system operator has to be able to communicate with the demand side manager such that they actually provide the appropriate flexibility whenever it's necessary. What is currently being developed is something which is called the Ampel model, or the traffic light model of grid management, where we have three different situations, where we have a green situation, where the market can operate, where we can do everything on the market. There are no bottlenecks in the system. Then a yellow situation would be a situation where we have some bottlenecks. And so here it says the priority signal greater 0. Up here I did not mention, but I have listed it here. A network control system which would generate a priority signal indicating that certain actions are necessary. And it may be that some demand side manager has to respond immediately to such a signal, or it may be that here, if the priority signal is greater than 0, that a certain action is desired but not immediately necessary. If it's just desired, the priority signal is greater than 0. You have some bottlenecks and you put requests on the market, get them from the network control system, and the demand side managers can then put their bits there and get selected to provide certain flexibility. And in the red phase, you have severe bottlenecks, and there you need direct control from the grid operator into the houses. Maybe you have to switch off certain solar panels. Maybe you have to switch off certain, like you would switch off solar panels if you have too much power generation. You would switch off heat pumps, for example, if you have too much demand. And these are phases where you have to respond immediately. And this is the current model for the grid operation that is just being developed. Green for free operation of the market, yellow slightly controlled, red means directly controlled. And this is visualized here. We have this structure that we have our, like down here we have our smart metering systems. Information from that, all our let's say, our organic smart home systems. We generate flexibility information. The demand side managers are getting that information, send it to some higher level, some kind of demand response here. We have the network control system. The network control systems makes predictions on the situation in the grid, and if there is a bottleneck indicated in red here, then they send a signal such that the demand side managers have to operate. If only slight bottlenecks are there, then the market is used to decide which demand side manager should actually be selected to provide a certain service, and the market will then select the demand side manager's bids depending on the prices at which they offer something. So this is some view on the system. Here's another one. The network, like here, the smart metering system. This is actually a result of the Meregio project, which has set the basis for this architecture, which is now transformed into this Ampelmodell. So we have our network control system, which is noticing a certain situation, looks at the aggregations. We have our metering data, which is collected in the data repository. Like such a request is sent to the demand side managers. The demand side managers would actually put information to the markets, and then the demand side managers would communicate with the markets, get selected, and would actually control the devices in individual buildings. So this just shows how different components here would communicate. I think it's more or less self-explaining. We have priority signals. This is the blue signal here, and if we have the priority signal greater 0, the market is in there. If it is 0, then the market is not involved, and it's going directly to the demand side managers. Okay, just very briefly, this is another view on a project that is currently running, grid control. Actually in German here, this picture. So what we do here is, again, based on the Ampelmodell. We have several different components. We have generators of power, we have demand of power, we have storage of power, and we have a Gebäudeenergiemanagement, building energy management system. We have a grid control unit. And now normally the building energy management system will control what's happening in the house. And in particular in the green and yellow phase, this is indicated by those two lines. We have the communication of the building energy management system with the BI stands for business, intelligence, EM, energy management system, and that will communicate with the DSO, Verteilnetzbetreiber, also business intelligence in the green and yellow phases. And in the red phase, the regional energy management system, which is under the control of the distribution system operator, will directly interfere using that line with the building energy management system or the grid control unit directly, and either switch off solar panels or maybe switch off heat pumps, for example. So this is showing the different interactions between the different stakeholders in the system, and this is currently being designed for another field test in the Black Forest area and at Freiamt. Okay, time is over for today. Next time we will look on other smart home solutions and then come to other topics. Okay, thank you very much for your attention.